Okay, so we're going to be graphing logs here. This isn't too bad. I'll do the basics. I could do the introduction. So basically, a logarithm is just the inverse of an exponential function. So in this case, of course, our standard form for exponential functions, or exponential, is y equals a times b to the x minus h plus k power. So if we were graphing y equals 2 to the x, we've talked about this. My x-intercept, well, this is never going to cross. There's no x-intercept because y equals 2 to the x. Well, this can never be equal to 0 because 2 to the x can never be equal to 0. So your y-intercept, while I go through my table, 2 to the negative third is 1/8, 1/4, 1/2, 1, 2, 4, and 8. So my y-intercept here is at 1. Asymptote, well, what you look at is what can, in this case, it's what can't y be? Well, y can never be 0, so my asymptote is going to be at y equals 0. For my logarithms, it's from negative infinity to positive infinity is the domain. My range goes from my asymptote. This is a growth function going this way, so it's going to be from 0 to positive infinity. If it was a function going this way, it would be negative infinity to 0. So, I'm going to graph my function to start with. So I have -3, then I have 1/8, then I have 1/4, then 1/2, then 1, 2, 4, and then 8. So there is my first function. Okay. Next thing I'm going to do is I'm going to graph the line y equals x, like this. So this is my little explanation of how these work. Okay, and then I'm going to graph my inverse function or graph the inverse of 2 to the x. Well, the inverse of 2 to the x is going to switch all this. So it's going to be 1/8, -3. So it's going to be at 1/8, it's going to be at -3. Okay, at 1/4, it's going to be at -2. Okay, at 1/2, it's going to be at -1. Sorry, at 1/2, it's -1. At 1, it's going to be at 0. At 2, it'll be at 1. At 4, it'll be at 2. Okay, and then at 8, it'll be at 3. So that's what the inverse of my function looks like. So I just switch my x and my y. We could just flip it over that graph. In this case, my x-intercept is going to be 1. My y-intercept is none. My asymptote, actually, instead of y equals 0, is x equal to 0. My domain is no longer a negative infinity to positive infinity. It's actually just going to be, it goes from 0 to positive infinity because it's my lowest value. And my range in this case is going to be from negative infinity to positive infinity. So what you need to know is that the x and y values, and features, I can spell features switch. And what this new graph is called, it is called a logarithm. Okay, so this is called this in the blue is called a logarithmic. Sorry, there's an extra I there. Function. And so actually the equation of this function right here, this is y equals log base 2 of x. So in a logarithm, instead of having your base, this is where your base is down here. Okay. This right here, this equation is actually, since it's the inverse of an exponential, this is actually 2 to the y is equal to the x, versus with our original function, 2 to the x is equal to y. Okay, this is the inverse, and this is just a special way that we write the inverse. It's called a logarithm. It's log base 2. Okay, because this is when we write it this way, this is actually in function form. But these two things, this here and this here, actually mean the exact same thing. So the inverse of an exponential, spoiler, is called logarithmic. Function. A logarithmic function is written as y is equal to log base b and then x, b to the x. This is called your base. This is actually the exponent, and then the y is my answer. This right here is the same thing as writing b to the y is equal to x. These are equivalent. And we're going to go back and forth this one here because this one's going to be much more familiar to you. A common logarithmic function is actually, a common logarithmic function is when I write y equals log of x. So what you'll notice is there's no base. Well, actually, the no base is actually base 10. This is the same thing as y equals log base 10 of x, okay? And then we'll rewrite this in exponential form because this is where, 10 is the base. So y is equal to log base 10 of x. I can rewrite this, that's actually 10 to the y is equal to x. It's graphing that function. And then we have something called a natural logarithm. A natural logarithm is kind of an interesting one. So y is equal to ln of x. This is called a natural log. I do not have a t-shirt for that. Okay, that is the same thing. Let me write this properly. That's the same thing as y equals log base e of x. E is a very special number. It's an exponential growth constant. It's kind of like pi. We approximate this as 2.71, but it is also in the calculator. And we'll talk about that. So that's going to be in your calculator. And then, of course, the exponential equivalent would be e to the y is equal to x. Okay, so again, these two things mean the same thing. We're going to graph y equals 10 to the x, and we'll graph the inverse. So we're going to kind of basically be, when we graph a logarithm, I'm going to start with a parent function. So for my first one here, I have, if I want to graph, let's say, my common logarithmic function, this is going to be y equals log base 10 to the x, okay? So I'm actually not going to look at this function. I'm going to, well, I know that if I write this as an exponent, this is going to be x is equal to 10 to the y power, which is very similar to y equals 10 to the x power. Now, what we're going to do is we're going to set up our table, except for this, you're actually going to start with your y values instead of your x, because this is the inverse. So typically we plug in our y values and then we find our x, or we plug in our x values to find our y values. In this case, because it's the inverse, we're going to plug y values in to get our x values. Okay, so when y is, let's say -1, we know that this is 1/10. When y is 0, this is 1. When y is 1, this is 10. When y is 2, my function is 100. And actually, we're focusing on that function right there. Okay, so it's kind of like when we start with a parent function here. So I graph that function. So it's going to be, all right, so it's going to be 1/10 and -1. So it's going to be here. It's going to be 1, 0, and then 10, 1, which is going to be somewhere around here. And so I have my rough little sketch of what it's going to look like, and that's about it. So that's what my parent function looks like for this one here. All right. So let's get to graphing. So we kind of have our foundations. We have our definitions, which is we have our natural log, we have our common log, and kind of what they look like. And we're just treating this as an exponential. So, so our first one here shouldn't be so bad. This is log base 4 of x. I'm going to write this in exponential form because it's more familiar. So remember, this is y is equal to log base 4 of x. Now this is still my base, so this is going to be 4 to the y power is equal to the x. So we do the same thing. I graph as if I were graphing a regular function, except instead of starting with x, I start with f of x and I do -1, 0, 1, 2, let's go with 3. So actually, you know what? Sorry. I'm going to do -2, -1, 0, 1, and 2. So when when y is -2, it's going to be 4 to the -2nd power, which is 1/16. So it's going to be low. 4 to the -1 is going to be 1/4. 4 to the 0 is 1. 4 to the 1 is 4, and 4 to the 2 is 16. And so I take these and I graph them. And so in this case, so it's going to be 116 -2. It's going to be 1/4 -1, 1, 0, 4, 1, and then 16 is going to be somewhere up there. And there we go. Okay. What we need to remember is if we're graphing this, remember that this can never be equal to, so you remember your exponential can never be equal to 0, so your asymptote, okay, when you write this, is x is equal to 0. Because this right here, 4 to the y, can never be equal to 0. So x can never be equal to 0, so that's where our asymptote is. Okay. For these, it's the reverse. This one right here has no, it has no y-intercept, but it does have an x-intercept at 1. My range is going to be -infinity to +infinity, and my domain is from 0 to infinity, and I have an asymptote at x equals 0, because instead our exponential functions had asymptotes at y equals. Since this is the inverse, they're going to have asymptotes at x equals. All right, so our next one is our natural log. We're just going to do a rough sketch. So if you remember, I said that this is y is equal to log base e to the x, which is around 2.71. This is where I give you a calculator, essentially, for these ones. So this is going to be e to the y is equal to the x. Okay. So I'm definitely going to do 0, I'll do -1, I'll do +1, and then we'll go from there. So when y is -1, okay, so when y is, so, sorry, I'm fumbling right now. So e to the -1 is going to be something really small. I'd let you use a calculator if I were giving this. So it's 0. So this is essentially going to be 1 over 2.71 because e is approximately 2.71. We'll go with, this would be 1 over 2.71, which is about 0.37. The 0 power is 1. To the first power is 2.71. So I'm just going to graph it that way. So it's going to be at 3.71, and this is going to be -1, -2, -3. This is 1, 2, 3, 4, 5. Okay, so 1.371, 1.37, -1, 1, 0, and 2.71, so close to 3, and about at 1 for this one. So there we go. So there's our natural log. It's just the same thing with weird numbers. X-intercept was at 1, y-intercept, of course, doesn't exist. We still have our asymptote at x equals 0 because it doesn't matter. Even if it's some weird number to y, I know that x cannot be equal to 0 in this case. My domain is going to be from 0 to infinity, and my range is from -infinity to +infinity. So, all right, just 2 more. Okay, so now we have a log base 2 of x plus 1 minus 2. Okay, I'm going to do the same thing that I've been doing with our transformations tables. So first off, this right here, it's going to be 2 actually, you know what? We're going to think about this differently. All right, so we are going to find a table for our parent function. So our parent function is going to be log base 2 of x, which is essentially 2 to the y is equal to x. So I start with my parent function table. Okay, and we kind of work backwards from that. So we have our -1, 0, 1, and 2. And I know that this is going to be 1/2, 1, 2, and 4. Okay, then we use our transformations on the inside. So in this case right here, this x plus 1 means that I'm going to take my x values and I'm going to subtract 1. And then here, this means I'm going to take my y values, or sorry, I'm not going to subtract. Yeah, I'm going to subtract 1 because I always do the opposite. So it's the opposite of what's going on the inside. So x minus 1, and then this is going to be y minus 2. So 1/2 minus 1 is -1/2. 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. And then we do y minus 2. -1 minus 2 is -3. 0 minus 3, or minus 2 is -2. 1 minus 2 is -1, and 3 minus 2 is 1. So let's graph this. Let's do 1, 2, 3, 4, -1, -2, -3, +1, +2, 3, +4. Okay, so our first point is, all right, at -1/2, -3, so right about here. And then we have 0, -2. And then we have 1, -1. Then we have 3, 1. Okay. In this case, I do have a y-intercept at -2. My x-intercept is kind of a little bit of a dicey thing. So remember, your x-intercept is where y is equal to 0. So I could rewrite this. It's going to be me getting into something a little bit more complicated than I wanted to. But this would be 0 is equal to log base 2 of x plus 1 minus 2. I'd add 2 to each side. 2 is equal to log base 2 of x plus 1. And then we could rewrite this. This is 2 to the 2 is equal to x plus 1. 4 is equal to x plus 1. Oh, that's because this is supposed to be 0. Of course it is. Sorry, that is a very Miss Hawley mistake. Just so I can show you algebraically. I'm sure you're sitting at home and saying, Miss Hawley, can't you see that you don't know how to subtract? Okay, there we go. So, and so x would have to be 3, which we know. So we could do this algebraically. So your x-intercept is at 3. My domain is, well, we're trying to figure out our domain. Well, here is our domain since this actually shifts. So where this is, where x plus 1 is equal to 0, that is going to be your asymptote. Okay, because you can never, this can never be equal to 0. So x is going to be equal to -1, so my asymptote is x is equal to -1. So my domain is going to be from -1 to infinity. My range is -infinity to +infinity. And I'm sorry I messed that up. But yeah, your asymptote, just like it's everything outside the x value, when you're doing your exponential, it's everything outside of your, everything outside with your y value for your domain or for your exponentials, but it's everything outside of the y value or the y value for the other one. So, okay, so this one's a little bit weird. Kind of the same thing, but we treat it exactly the same way essentially. So we start with our parent function, log base 3 of x, y is equal to, I think if I stop talking that would be better, y is equal to log base 3 of x. So this is 3 to the y is equal to x. So we start with our parent function, -1, 0, 1, and 2. That's going to be 1/3, 1, 3, and 9. Okay, so I look at what's happening here. So we're going to have 2 tables because actually 2 things happen with our x. I also, for my asymptote, 2x plus 1, we want to know when that is equal to 0. Okay? Because that'll tell, for our logarithm, it's always what the inside of your log is equal to 0. I'll get to that in class, exactly why that is the way it is, but you always set this equal to 0 to find your asymptote, what's on the inside. I know. So this would actually be, my parent function would be 3 to the y is equal to 2x plus 1. 2x plus 1 could never be, this right here can never be equal to 0. So that's why we would use our asymptote to show it in exponential form. Anyway, so I'm going to do 2 tables. So the first thing I'm going to do, I always follow order of operations. I would So I'm going to take my table, my x and my y. I'm going to subtract 1 from all of my x values. So this is going to be negative 2/3. 1 minus 1 is 0, didn't get me this time. 3 minus 1 is 2. And 9 minus 1 is 8. Because this was 2x plus 1, you're going to subtract 1 because it's going to be the opposite, and you follow order of operations. Your y values didn't change any. 1 and 2. I'm going to do a second table because we also have that 2x, okay? But instead of 2x, I'm actually going to take all of my y values and I'm going to multiply by 1/2 because it is always the opposite and inside. It actually has to do with solving. So my y values again stay the same, 0, -1, 0, 1, and 2. And then I do half. So negative 2/3 times 1/2 is going to be negative 1/3. Okay, 0 divided by 2 or times 1/2. Okay, 0 times 1/2 is 0, 2 times 1/2 is 1, and 8 times 1/2 is 4. So, -1, -2, -3, 2, 3, 1, 2, 3, 2, 3, 4. Sorry, 4 here. Okay, so negative 1/3 and negative 1. Is right about there. 0, 0. 1, 1. And 4, 2. And we have our asymptote. I forgot to do our asymptote with this guy. This asymptote was at -1. This right here, well, when is 2x plus 1 equal to 0? When x is equal to -1/2. So we have a little asymptote at negative x equals -1/2. So our y-intercept is at 0, 0. Our x-intercept is at 0, 0. I know. I didn't write them as points. X-intercept is 1, 0, 1, 0, 3, 0, 0, -2. My domain is from -1/2 to infinity, and my range is from -infinity to +infinity. And that is essentially how you graph a logarithm in a nutshell. So it's pretty basic. You just have to basically treat it like an exponential. Instead of doing x as your input, you do y as your input. So it shouldn't be too bad. That's about it.